Welcome to my talk. I would like to thank Professor Anu Varghese for inviting me to be a speaker in this conference, and also to Professor Ambat and the organizing committee and everyone who has organized this online conference. So before we start, we first need a little background on chemistry, especially with regards to the conduction and insulation of molecules, of the atoms that connect, that are connecting together to form the molecule. Don't worry, this won't be too complicated, I hope, but we do need this in order to understand the mathematics that follows. So then after this, we'll start having fun with mathematics, I hope. We distinguish between molecular and chemical graphs in this talk. A molecular graph is a graph that represents a molecule, basically. So the vertices of the graph are the atoms of the molecule, and the edges are the bonds that keep the molecule together. So a pi system contains carbon atoms connected by single and multiple bonds. The single bonds are called sigma bonds, and the multiple bonds are pi bonds. So sometimes multiple bonds can be double bonds or triple bonds. Those are the usual bonds that you can have if you have multiple bonds. A chemical graph is a graph whose vertices represent the unsaturated carbon atoms of a pi system. What do I mean by an unsaturated carbon atom? If you have a carbon atom, carbon atoms like to bond with 4 other atoms. And when that happens, the carbon atom is saturated. Now, in an unsaturated carbon atom, the carbon atom bonds itself to 3 or 2 other atoms instead of with 4 atoms. That's what unsaturated means. Because of this, chemical graphs cannot have degree more than 3. And this is the main difference between a molecular and a chemical graph. A molecular graph represents a molecule that can have any vertex degrees, whereas a chemical graph must have degree at most 3. Let's give an example then. So we have diamond here and graphite. They are both carbon molecules, as you might know. In the case of diamond, the structure of the carbon atoms is tetrahedral, as you see here. And each carbon atom is bonded with 4 others, as you see here. So each carbon atom is bonded with 4 other atoms. Because of this, this does not have conduction, because in order to have conduction, you need to have degree at most 3, and here the degree is 4. So because of this here, we don't have unsaturated carbon atoms, which leads to no conduction in the molecule. So this is not a chemical graph. In the case of graphite, the carbon molecule in this case has the following structure. As you can see, it's like various layers of hexagonal lattices. And here, each carbon atom is bonded to 3 other carbon atoms. Note that these dotted lines here, those are not sigma or pi bonds. Those are just weak bonds that kind of scrape themselves when you even touch the graphite. In fact, we use graphite for the lead of a pencil, like this one. The tip of the pencil, when you write something down, these hexagonal layers are scraped off and they're left on the paper so that they leave the markings that you want to leave on. Now, the point here is not that, though. The point here is that since we have three, the degree is 3 at most, we do have conduction here and we have an unsaturated system, which means that here we can look for the conduction of the atoms, between atoms. So we have a chemical graph, as we said, and we're going to represent it by its 0, 1 adjacency matrix as usual. Note that the carbon atoms only are taken into consideration. So if we have a hydrocarbon, for instance, which has carbon and hydrogen atoms, we only look at the carbon atoms of the molecule and represent the connections between these carbon atoms only by the 0, 1 adjacency matrix, as we usually do in graph theory. The nullity of a graph, which we're representing it by eta of G, in chemistry has the following interpretation. They say that it's the number of non-bonding orbitals in the molecule. Now, what is the SSP model, or the source and sink potential model? In this model, electron transmission at the Fermi level, which means when you have the eigenvalue 0 between two semi-infinite wires connected to any two carbon atoms, is determined by four nullities, basically. The nullity of G itself, the nullity of the graph when you remove vertex U, the nullity of the graph when you remove vertex V, and the nullity of the graph when you remove both vertices U and V. When you attach the wires to the same atom, then the connection is called ipso. Now, of course, you're realizing that connecting wires to atoms is practically impossible. So that's why we use the SSP model to predict what's going to happen. And this leads us to omniconductors and omni-insulators. In the case of a distinct omniconductor, we have a molecule where conduction at the Fermi level occurs for all distinct pairs of carbon atom connections. In the case of an omni-insulator, you have exactly the reverse. Insulation at the Fermi level occurs for all distinct pairs. This happens when you have a distinct omniconductor or a distinct omni-insulator. When you have an ipso omniconductor or an ipso omni-insulator, you have conduction or insulation at all single carbon atom connections. Otherwise, it's the same definition as before. If we have both a distinct and an ipso omniconductor or omni-insulator, then we call them a strong omniconductor or a strong omni-insulator, respectively. The question now is whether these omniconductors or omni-insulators exist. And we have the following list of results from the paper Omniconducting and Omni-insulating Molecules by the authors written on the slide. So the first result is that there are no distinct omniconductors whose nullity is greater than or equal to 2. Ipso omniconductors exist both when they have nullity at most 1, and there are also ipso omniconductors having nullity at least 2. Strong omniconductors then, by the previous two results, can have only nullity at least 2. Now what about the insulators? There are no distinct omni-insulators having nullity at most 1. There are no ipso omni-insulators having nullity 1 or more. So this is telling us that ipso omni-insulators exist only when the nullity is 0. And finally, if we combine the previous two results, we have the pretty useful result that strong omni-insulators do not exist. So let's leave chemistry for a moment and focus on knot graphs. What is a knot graph? A knot graph is a graph whose definition was introduced in 1998 by Shriha and Gutman. A knot graph is one that has nullity 1 and whose kernel eigenvector has non-zero entries throughout. So that's a knot graph. The smallest chemical knot graph is the one shown here. And these numbers next to each vertex are, in fact, the entry in the corresponding kernel eigenvector, which, as you're seeing, are all non-zero. Now, why did we introduce knot graphs? Because of this result. If we have a molecule with nullity 1, then it is a distinct and strong omniconductor if and only if it is a knot graph. And this is interesting because knot graphs, as I said before, were invented in 1998, but you could say that the first application of knot graphs was only found in 2014, so that's 16 years later. In the case of ipso omniconductors having nullity 1, this is not necessary and sufficient. There are some of them that are knot graphs, and there are others that are not knot graphs. Let us now focus on graphs having nullity 0, which means that they are non-singular, they are invertible. In chemical terms, they have no non-bonding orbitals. This result is very, very important for what follows in this talk. Insulation at the Fermi level for a non-singular graph occurs if and only if the corresponding entry in the inverse is 0. And this is true both when U and V are distinct and when U and V are the same. So in the case of a non-singular graph, we have the following results. A distinct omniconductor will exist when the entries outside the diagonal of the inverse are all non-zero. An ipso omniconductor will exist if the entries in the diagonal of the inverse are all non-zero. Of course, for ipso omni-insulators, you have exactly the reverse. The entries in the diagonal of the inverse are all 0. And finally, strong omniconductors that are non-singular have this property that the inverse contains no 0 entry. Note that the other two possibilities, which are distinct omni-insulators and strong omni-insulators, do not exist for non-singular graphs, as we said before. This is an example of a non-singular strong omniconductor. It's the Buckminster-Fullerene C60, which, as you're seeing, has the shape of a soccer ball, or if you are not from the US, a football. We say it's C60 because it has 60 carbon atoms that form this molecule. Note that in the second picture, wherever you have double lines, those are double bonds, so pi bonds. When you have single lines, like in this pentagon, for example, those are sigma bonds or single bonds. Now, if you were to take the adjacency matrix of this graph, so a 60 by 60 matrix, and you were to find its inverse, first of all, the inverse exists, and secondly, the inverse will contain exclusively non-zero entries. In chemical terms, this makes it a strong omniconductor because its inverse has this property. So in the case of this molecule, it means that if you attach two wires to any two vertices, then you get conduction whether those vertices were different or whether they are the same. You still get conduction. As we said earlier, all ipso-omni insulators are non-singular. There are no examples of ipso-omni insulators that have nullity greater than 0. And if you were to try to find examples of such ipso-omni insulators, there are in fact plenty, because all non-singular bipartite graphs are ipso-omni insulators. And one way to realize this is to use a little spectral graph theory. As all of us know, a bipartite graph has its spectrum symmetric around 0. So if it is non-singular, it does not have a 0 eigenvalue. But if you remove one vertex, then it must be the case that it has a 0 eigenvalue, because now you have a different parity of the number of vertices. And this 0 eigenvalue gives us a 0 entry in the corresponding diagonal of the inverse, which makes it an ipso-omni insulator. This is an example of an ipso-omni insulator. It's benzene, which is C6H6. As we said earlier, we ignore any atoms that are not carbon, so we're ignoring these white atoms here, which are the hydrogen atoms, and we're only focusing on this carbon skeleton, which, as you're seeing, is simply a cycle on 6 vertices, which is, of course, a bipartite graph, so it is automatically an ipso-omni insulator. An interesting thing that we could do now is combine these properties of omniconductance and omni-insulation together. And in the case of non-singular graphs, this can only be done for distinct omniconductors and ipso-omni insulators, because distinct omniconductors have a non-zero entry outside the diagonal of the inverse, whereas ipso-omni insulators have a 0 entry within their diagonal. In the case of strong omniconductors, we have already shown that there are quite a few, like, for example, C60. Unfortunately, in this case, for this case, having a molecule that is distinct omniconductant and at the same time ipso-omni insulating as well, only one graph could be found, which is a very trivial graph, K2. So the authors of the following paper, Interlacing Extremal Graphs, called these molecules nuciferous graphs. So a nuciferous graph then is a non-singular graph whose inverse has non-zero entries outside its diagonal and zero entries within its diagonal. And the question was whether there are other nuciferous graphs apart from the trivial one K2. The authors of the paper I've just mentioned concluded the paper by making this conjecture. The conjecture that the only nuciferous graph is K2. So they conjectured basically that there are no other nuciferous graphs. The point now is we want to find other nuciferous graphs or perhaps prove this conjecture to show that there aren't other nuciferous graphs apart from K2. Okay, so that concludes the chemical part of the talk. Now we have only mathematics. And as you realized, we are going to try to prove that there aren't any other nuciferous graphs, or perhaps prove that there are other nuciferous graphs. So that's the point of the next two parts of this talk. To do this, we need to introduce what we call non-singular graphs with a singular deck. And these graphs are not simple because they have weighted edges. The reason for this will become clear later. And we define an SSD or a non-singular graph with a singular deck as being a weighted non-singular graph having singular vertex deleted subgraphs. Now, this idea is similar to what we talked about earlier when we mentioned the bipartite graphs, and in fact, SSDs can be bipartite, as we shall see soon. Before we continue, a few notes. Since we've just said that every vertex deleted subgraph is singular, then the inverse of the matrix will have a zero diagonal. So if the graph is simple, any NSSD represents an ipso omni insulator. Note that having an ipso omni insulator is half of what we want, half of the nuciferous graph, if you will, because a nuciferous graph is also a distinct omniconductor. Earlier, we also mentioned NUT graphs, and in a sense, they are the opposite of an NSSD. Why? A NUT graph, just a little reminder, is a graph whose nullity is 1, and the kernel eigenvector x has non-zero entries. So clearly, a NUT graph cannot be an NSSD. Since all entries of x are non-zero, the nullity of the vertex deleted subgraphs of a NUT graph must all be less than that of G, because every vertex in a NUT graph is a core or lower vertex. So the nullity of every vertex deleted subgraph of a NUT graph is 0, which means that a NUT graph is a singular graph with a non-singular deck, exactly the opposite of an NSSD, which is a non-singular graph with a singular deck. We still haven't said why we have decided to define NSSDs having weighted edges and not edges having only weight 1. Since an NSSD is non-singular, its inverse exists, of course. And this means that when you have an NSSD, the inverse exists and also must have no loops, because we want the zero, we want zeros in all the diagonal entries of the inverse of the NSSD. But now, if we consider this inverse to be a graph itself, then the inverse of the inverse will be the NSSD itself. And this tells us then that G, a graph G, is an NSSD if and only if its inverse is an NSSD. But we can only say this if we allow weighted edges. So that's why we decided to define NSSDs having weighted edges. In this way as well, we have a duality. If we want, we can consider G as being the NSSD, and sometimes we can shift our attention to its inverse so that we find properties also on the original graph. And not only that, we have the peace of mind that the inverse is also an NSSD, so it has the same properties. If it were a 0-1 matrix, it would be an ipso omni insulator. Let us give an example of an NSSD. So the graph on the left, this one, is an NSSD. Notice that we have these weighted edges for these two edges, the edge 1, 4 and the edge 1, 5, whereas the others are assumed to have weight 1. If we don't have any number corresponding to an edge, then that edge has weight 1. The graph on the right, on the other hand, is its inverse, which, as you're seeing, has no loops. And that is the defining thing about NSSDs. If you find the inverse of an NSSD, it won't have any loops. Note that for the inverse, we have many more edges having weight not equal to 1, but that's fine. And NSSDs can have weighted edges, so that is okay with us. By the previous theorem, this inverse is also an NSSD. So these are inverses of each other, and these are both NSSDs then. A few results on NSSDs. The vertex deleted subgraphs of NSSDs have nullity 1. This is a consequence of the interlacing theorem, which allows only a change in multiplicity of one more or one less, or leaving the multiplicity the same when you remove a vertex. So in the case of an NSSD, since it is by definition non-singular and its vertex deleted subgraphs are singular, there's no other nullity that the vertex deleted subgraphs can have apart from 1. What is more interesting is what happens when you remove two vertices from an NSSD. And this is really important for us because when you end up with a non-singular matrix, when you remove two vertices, that happens exactly when the entry in the inverse at u and v is non-zero, which means, in other words, that the inverse NSSD has an edge there. On the other hand, it is singular of nullity 2, it cannot be of nullity 1, when this does not happen, in which case you don't have an edge in the inverse. Or alternatively, you could say that the inverse matrix has a 0 in the entry uv. Of course, here we're assuming that u and v are different vertices. So suppose we have an NSSD whose two vertex deleted subgraphs have the same nullity. By the previous result, this nullity can either be 0 or 2. But this nullity cannot be 2. Otherwise, the inverse will be the 0 matrix. And the 0 matrix does not have an inverse itself. So this means that if we have an NSSD whose two vertex deleted subgraphs have the same nullity, then this common nullity is 0. Now let's think about this. So we have an NSSD whose nullity is 0. Its one vertex deleted subgraphs has nullity 1. And in this case, we have the two vertex deleted subgraphs that have nullity 0. But we have already said that in the case of a NUT graph, we have a graph whose nullity is 1 and whose vertex deleted subgraphs are of nullity 0. This is why we defined a NUT full graph as being such an NSSD, because its vertex deleted subgraphs are NUT graphs, except that these NUT graphs may have weighted edges. So instead of calling it nuciferous, we called it NUT full. In fact, this theorem is basically telling us what we've just said, that G is NUT full if and only if G is an NSSD and its inverse is a weighted complete graph with no loops. So a little terminology then, what we're looking for, which are nuciferous graphs, are simply simple NUT full graphs. So NUT full graphs whose original graph is simple. It has only zeros and ones in its adjacency matrix. The vertex deleted subgraphs of a nuciferous graph are NUT graphs. And that is from where the word nuciferous comes from. Nuciferous means not producing. And in fact, these are not producing because when you remove any vertex from a nuciferous graph, you end up with a NUT graph. Okay, then a little summary. So we have NSSDs whose weighted adjacency matrix and their inverses have both zero diagonals. That's an NSSD. When you have an NSSD, its inverse is an NSSD as well, and vice versa. A NUT full graph is an NSSD whose inverse has non-zero entries of its diagonal. So apart from having zero entries on its diagonal, it has non-zero entries of its diagonal. This means that a complete NSSD is a graph whose inverse is a NUT graph. Sorry, is a NUT full graph, because basically by combining these two points together. So the complete NSSD here is taking the role of the G to the -1, is taking the principal role. Then when we take the inverse, we get a NUT full graph. A nuciferous graph is a simple NUT full graph. So a NUT full graph which does not have weighted edges. So how do we find nuciferous graphs then? We can find nuciferous graphs perhaps by looking for complete NSSDs. If we find a complete NSSD, which means a complete graph with weighted edges, that is an NSSD, so whose inverse has zero diagonal, the inverse I've just mentioned will be a NUT full graph. If it so happens that this NUT full graph is not weighted, then we would have discovered a nuciferous graph. So that's what we're going to do now, trying to find complete graphs, complete NSSDs rather. The first result, there are no complete NSSDs on 3, 4, or 5 vertices. In fact, there aren't any NSSDs at all with 3 or 5 vertices. But we do have NSSDs that are complete for any n at least 6, where n is the number of vertices. So there are complete NSSDs on 6, 7, 8, 9, 10, and so on vertices. And by taking the inverse, not full graphs on 6, 7, 8, etc. vertices exist for any n. Unfortunately, we still couldn't find Lucifer's graphs. We found a lot of not full graphs, but we did not find any Lucifer's graphs. This result helped us tremendously though. So what if we remove 3 vertices of an NSSD? Then the nullity of the resulting graph will be 0 if these 3 edges form a triangle in the inverse. The nullity is 3 if these 3 edges are not present in the inverse. All of them are not present in the inverse. Otherwise, if there are 2 or 1 of these 3 edges in the inverse, then G minus U minus V minus W will have nullity 1. So nullity 2 is never there. It doesn't. There are no 3 vertex series subgraphs of NSSDs having nullity 2. And this allowed us to prove that no not full chemical graph exists apart from K2. Not just Luciferus, even not full. Remember, a chemical graph is a graph that has a degree at most 3. Let us give a sketch of the proof. So let G be a not full graph that is not K2, and let V be one of its vertices. We also assume that G is connected. If it's not connected, then each component will be an NSSD, and we can prove this on each component. First, suppose our graph has a vertex of degree 1. So suppose this is the graph G that has this vertex B here of degree 1. So it is connecting to only one other vertex U. Now, vertex U itself must connect to at least one other vertex. Let's call it W. And this is the case because otherwise G would be disconnected. Now, suppose we delete vertices U and W from G. So we delete these vertices, and the resulting graph G minus U minus W will have this part on this part here, and then it will also have this isolated vertex. This means that G minus U minus V cannot have nullity 0, so it must be of nullity 2. But when that is the case, the inverse will have a non-edge between U and W, which means that the inverse is not complete, and hence the original NSSDG is not full. Now suppose V is of degree 2. So once again, let's draw something. We have the graph G, and U has degree 2, or V has degree 2. So we have vertex V here that is connected to 2 other vertices. Let's call them U and W. Okay. Now, if we immediately remove U and W, so we remove these, once again, we end up with the same thing. We end up with this isolated vertex. So the same argument holds. G minus U minus W is of nullity 2, which means that the inverse matrix must have a non-edge between U and V, so it is not complete. So the original graph wasn't not full after all. Now suppose we have our vertex V of degree 3. So once again, we have our graph G with our vertex V and 3 other vertices this time that V is adjacent to. Let's call them U, W, and Z. Okay, and we do the same thing. We delete these 3 vertices U, W, and Z, and we end up with the graph G minus U minus W minus Z, which has nullity at most, nullity greater than 0. Because of the theorem we have just shown before this proof, the resulting graph in the inverse must have at least one of the three edges in the triangle UWZ, which is not there, which is non-existent, meaning that g to the minus 1 is not complete, and hence g is not full. So this means that if we have a not full graph, none of its vertices can be of degree 1, degree 2, or degree 3. So it cannot be a chemical graph. In fact, we can say something even stronger, because in a chemical graph, all vertices must have degree 1, 2, or 3. But here we're saying that none of the vertices can have degree 1, 2, or 3 in order for a graph to be not full. But are there Nicephorus graphs that are not chemical graphs? The answer is yes. Gorbani provides the following list of graphs in the paper Non-Trivial Nicephorus Graphs Exist. Note that all of these graphs are Cayley graphs having these groups. For example, the first one has order 24, it has 24 vertices. There is one Nicephorus graph of this order and this group, and it has degree 15, etc. Note, however, that all degrees here are all greater than 3. So this confirms that no chemical Nicephorus graph exists, but there are, in fact, examples of Nicephorus graphs that have degree greater than 3. So that settles that conjecture. The final part of the talk will be about NSSDs themselves. The first result is this one. So suppose we have a graph with a terminal vertex, meaning it has a vertex of degree 1, so something like this. Here we're saying that V is the terminal vertex, so this is V and this is U. Then in the inverse, we still have a terminal vertex, so this is the inverse, g to the minus 1. But the terminal vertex this time will be the one that was adjacent to in G. So this time we have V and U instead of U and V. So that's the first result. The second result tells us that if we have any NSSD and we coalesce a path P3 with one of the vertices in G and the terminal vertex of P3, then you end up with another NSSD. So this tells us immediately that the number of NSSDs is infinite. We can continue doing this as much as we like. Another result tells us that if we start from any NSSD and we attach a pendant vertex on each vertex of G, then we end up with another NSSD. Moreover, if we have two NSSDs and we choose a vertex from the first and a vertex from the second, and we join them by an edge, then the resultant graph is also an NSSD. So this also confirms that the number of NSSDs is infinite. These are examples of non-bipartite NSSDs. They have quite a few vertices. Note also that these NSSDs are simple, which we call them molecular NSSDs when they are simple, because they represent some ipso omni insulator. Also, these graphs are all chemical. So far, we have constructed NSSDs by adding vertices. What about trying to find NSSDs from within the NSSD itself? Some subgraph of an NSSD. Can it be an NSSD as well? Earlier we said that G minus U minus V is non-singular if UV is an edge in the inverse. So what if it is not only non-singular, but an NSSD has a singular deck? That happens if UV is an edge, so that it's non-singular, then G minus U minus V. And also, that edge does not lie on a triangle in G to the minus 1. What if we add two pendant vertices, one to U and one to V in G? It turns out that the resulting graph is an NSSD when the same exact conditions for G minus U minus V happen, which means that UV is an edge in the inverse that is not on a triangle. As a corollary to this, if we have an NSSD with a pendant edge like we drew earlier, so we have a graph with a pendant edge, which is an NSSD like this, then both G minus U minus V and when you add the two pendant edges to U and to V, those are both NSSDs. And the reason is because we said that the inverse of this graph, which is G to the minus 1, will also have a pendant edge, but with V and U swapped, which means that the edge UV in the inverse exists, it's there, and it's also not on a triangle, which means then that G minus U minus V and the pendant edges attached to U and V are also NSSDs. Let us revisit this example where we have two NSSDs that are inverses of each other. Since this edge is a pendant edge, if we remove vertices 4 and 6 from this graph, we end up with an NSSD. The same thing is true if we do the same thing for the inverse. What we end up with if we remove vertices 4 and 6 from the inverse is also an NSSD. In fact, it would be isomorphic to the one that we end up with when we remove the two vertices from G. Now, notice, for example, as well, that in the inverse, there is no edge from 2 to 4. This means that if I remove vertices 2 and 4 from G, then I do not end up with an NSSD. In fact, I should end up with a graph of nullity 2. Moreover, if I try to remove vertices 1 and 2 from G, in the inverse, vertices 1 and 2 are not on a triangle. There is no triangle that has this edge on it. This tells me that removing these two vertices in G gives me an NSSD. On the other hand, for example, if we remove 3 and 6 from G, then we end up with a non-singular graph, but it is not an NSSD because these two vertices in G to the minus 1 do have an edge, but that edge is on this triangle 3, 5, 6. Let us mention bipartite NSSDs briefly. We have already mentioned them. They must have an even number of vertices, of course, because any bipartite graph on an odd number of vertices is singular. If G is a bipartite NSSD, then so is its inverse. This can be proved by looking at the matrix structure of a bipartite graph. When you take its inverse, it will still have the same structure. An interesting theorem is that when we have a tree, an NSSD tree, then its perfect matching is shared by its inverse, which may not be a tree. Moreover, these edges will be the only common edges of the two inverses, or of the two NSSDs. Here is an example. Here we have a tree simply depart on 6 vertices, which has these 3 edges as a perfect matching. Note that they are also a perfect matching of this bipartite graph, which is not a tree, which is the inverse of the leftmost graph. Also note that these 3 edges are the only 3 common edges in both graphs. There's also a way to construct NSSDs edge by edge. I'm going to explain this using an example. So suppose we start from the path P6, this one here, and we know it's an NSSD because it's a non-singular bipartite graph, and we want to construct further NSSDs from this by adding or removing edges. Suppose, for example, we want to add the edge 1, 4. Would the resulting graph be an NSSD? What we need to check is the following. We need to check if there is an edge between 1 and 4 that has a weight not equal to -1. In this case, unfortunately, we have an edge of a weight -1, so automatically this means that if I add an edge between 1 and 4 here, the resulting graph is not an NSSD. But in the case of, for example, adding an edge from 1 to 6, here the edge is not, in the inverse, the edge is not of weight -1, so that's fine. But we need also a second condition. We also want that these 2 vertices do not have a common neighbor. In this case, these 2 vertices in the inverse indeed do not have a common neighbor. There's no vertex that is adjacent to both. So that tells us that we can indeed add that edge to our NSSD to produce another NSSD. And we can continue doing so. For example, here we can add edge 1, 4 now, because this edge is not of weight -1 this time, and there is no common neighbor for 1 and 4 in the inverse, so that's fine. We can now, for example, delete edge 2, 3. To delete edges, we can do the same thing, except that we want that the edges between 2, the edge between 2 and 3 in the inverse does not have weight 1. In this case, we do not even have an edge, so that's fine. Once again, 2, 3 do not have a common neighbor in the inverse, so we can remove that edge. And we can also add edge 2, 4 to this graph for the same reason. There are other papers that contain NSSDs. These are 2 of them. One, the first one, notes that certain conference matrices arising from regular 2 graphs happen to be complete and not full NSSDs whose inverse is themselves. And in the very recent paper, outlined in the second part of the slide, we have another way of producing molecular NSSDs from the commuting graphs of hyperstructures called HP groups. I'm ending this talk here by showing you this quote by David Hilbert, which I think is very appropriate for this conference. Thank you very much.